All right. Hello, everyone. Hope you enjoyed your week off, sort of. I hope you didn't take it completely off, but it was very sad that I had that video for you and then it turned out that it had no audio, but yeah, basically it's okay. We can rearrange some things, compress some things, whatever, it'll be fine. So I just want, but basically we're gonna keep talking about asymptotic analysis today. I'm gonna basically go through what was in that video, but like with sound. So so basically what I want to do, like we know the definition of, big O, big theta, big omega, and we kind of, we saw some ways to like figure out things are. What I want to do now is we're just going to sort of go through, I call it a zoo. Basically like here's a bunch of common, like O of 1, O of log n, O of n squared, just go through a bunch of common things that we see and look at some examples of each, and then also like along the way we'll prove a few theorems about kind of how things are organized. Asymptotic complexity zoo. Alrighty, so number 1, constant time. Oops. Theta 1. Right, of course we could say theta 6, theta 1/2, it doesn't matter, we just say 1. So this is things that don't depend on the size of the input at all. Can anyone think of examples? What are things that like take constant time? Simon?
Checking if the number is even or odd.
Yeah.
Assuming it's stored in binary.
Yeah, because you just have to look at the last bit. Okay, what else?
Accessing an array element in a particular index.
Yeah, so good. Accessing an array index. So this is really important, and this is the foundation of lots and some other things. Does anyone know why? Like, why is it that you can access any index in an array in constant time? Like, it doesn't matter how big the array is, you can get a specific element right away. Anyone know why that works?
Take the memory location of the beginning of the array and just add the index.
Right, yeah. Exactly. Because the way we store arrays is arrays are stored in a contiguous chunk of memory. Like it has to be like laid out in consecutive locations in memory, and every element takes exactly the same amount of space. So you just have to do some math, a constant amount of math, right? You're like, oh, I want index, 49. You're like, okay, well, here's the memory address where the array starts. I know how big each thing is. I multiply by 49, and I just go there, right? I don't have to like go through it. Now, okay, is it really though? We usually assume that it is. However, like when if the size of your array is really, really, really big, then technically it's not constant time really, because like you can't even store the whole thing in one place. You have to like, store it on other computers, and like now it takes longer to access them. So I think there's a funny argument that in reality it's something like cube root of n, because like even if you stored your data like in a sphere, like the time it takes to get just to send a signal to where the element is stored and get it back like grows the bigger that your data is. Anyway, but it's constant. For all the arrays that we would care about, it's basically constant. Yes.
Could you not put it in like a 4-dimensional and 5-dimensional and so on sphere?
Yeah, I mean, if you know how to construct a 5-dimensional sphere. So actually, and it might even actually a 3D sphere might not work because of like heat dissipation. Like it's gonna, You might only be able to get away with like a circle, but anyway. This is actually one of the big problems if you want to make like really big chips, and like if you want to use, make them smaller, like you want to start stacking things, but you have a real problem with getting rid of all the heat that's generated. You just like fry your things. All right. What else takes constant time? So you're going to have to like dig back and think about data structures here, right? What are some other operations that take constant time? Or like data structures that have operations that you can do in constant time?
Off an element off of a heap.
Yeah, so well, not a heap actually, but like popping or pushing or popping from a stack. That's a good example. I mean, it depends on how you implement it, but all sensible ways of implementing stacks let you push and pop in constant time. And there's a bunch of data structures that let you like add and remove stuff in constant time, right? A very important data structure that lets you do stuff in essentially constant time is hash tables, right? So like insert or lookup in a hash table. Now this also, kind of like accessing an array index, has an asterisk next to it. This is a fatter asterisk than the array thing, but because like, well, what happens when your hash table is really big? What happens when you start having collisions? You have to like, but like basically on average, it's constant time. Okay, cool. Next thing I want to talk about is logarithmic time. This is like theta of log n. So, right, this basically has to do with like anytime that you are repeatedly having something, right? If you find logs confusing, and you're like, I'm never sure when it's log or something. If you just memorize this, logs have to do with repeatedly having stuff. Then that'll get you like 90% of the way, right? Anytime that you're taking something and then you're cutting it in half, you're cutting it in half again, cutting it in half again until you get down to one thing, right? The number of times you have to cut it in half, that's the log base 2, right? And of course, if you, instead of half, if you do like, oh, I divided by 3 every time, well, that's the log base 3 and so on, right? So what are some examples? Anyone have examples of things that take log n time?
A binary tree.
So doing what?
Accessing a binary tree.
Yeah, so like looking up in a binary search tree. I guess really there's an asterisk that it has to be a balanced binary search tree. If it's unbalanced, like if you just get like a big chain going off to one side, that's not log time. Okay, what else? What else takes log time? There's a kind of search that takes long time. Multiplication. No, that takes longer than log n. What was that?
Like in terms of the size of the numbers.
In terms of the size of the numbers. Well, the number of like log n is like the number of bits you need to represent a number, right? So number of bits to represent n, right? If your number is n and you're like, how many bits do I need? It's log. I was thinking of binary search, like when you have a sorted array, right? And it's just you can like look in the middle, and then depending on whether it's too big or too small, you can like throw away half of it and just look next half. Remember this from data structures. Okay. And actually, you know, over here in this column, I'm going to write the right column. I'm going to say the biggest n we can process in 1 second. In other words, like, you know, if you have an algorithm that takes, you know, log n time or theta 1 or theta n squared or whatever, I'm not gonna like go through the derivation, and you're gonna play with this on your homework, but like, what's the biggest size input you could have and be able to run that algorithm and have it take about 1 second, right? So okay, if it's constant time, then of course, you know, it's like infinity. Like, it doesn't matter how big your input is, it's constant time. If you have a log n time algorithm, right? Anyone want to guess, what do you think is like the biggest n that you could deal with and run your log n time algorithm and have it take, you know, at most 1 second? Anyone want to guess? It's bigger than 2.
We don't have the time.
2 to the power of the amount of operations you can do.
2 to the yeah, well, how many operations can you do in 1 second? I guess I haven't told you that, but that's great. Yeah. So 100 million is a good rule of thumb for like how many operations your computer can do in 1 second. So yeah, 2 to the 100 million, which is unimaginably large. So I was thinking about this earlier. So like, if you take the number of atoms in the visible universe, okay. Now, imagine that every atom in the visible universe contains another copy of the entire universe inside it. Okay, so like you zoom in on an atom and like there's a whole universe in there, right? And then that universe, like inside one of those atoms, well, each one, of course, there's like lots of them, right? One for each atom. Inside each of those, you zoom in, every atom in that universe has another copy of the entire universe inside of it, okay? And you do that about 1 million times. That's how big you could process in a second if your algorithm is log n. But I mean, the point is, it really doesn't matter how big your input is. If you have a log n algorithm, it's going to be like pretty much instant. Like, if you have a list of every human on Earth sorted by something, I don't even know how you would do that, but whatever. And you wanted to find like one specific person, right? And you'd use binary search. You'd only have to do binary search. You'd have to do about 32 steps worth of binary search to find the one person, which, you know, would just instantly. So yeah, if you have a log time algorithm, that is fantastic, right? It's not constant, but it might as well be constant in some sense because it's very small. Okay, here's an interesting theorem. Oh, no, before I say the theorem, I'll say note. Does anyone remember, you probably don't, and it's okay. So there is a formula for converting the base of a log. Simon, you actually remember this?
I actually used it in my home.
Oh, nice.
It's convert to log base C.
Yeah.
Log base C of n over log base C of A.
Right. So it doesn't matter if you remember this formula, but this formula exists, and you may remember that there was some way to like convert bases between logs, right? But the point is, what is this? So this is log base A, and this is log base C, and I'm then divided by something, which is really, I can like kind of factor it out like this. Right, so log base A of n is this thing times log base C of n. But notice this thing here, 1 over log base C of A, that doesn't have n in it. It's just a constant. Right, so this is a constant. Right, and when we're talking about big O, big theta, whatever, we don't care about constants, right? So from the point of view of big O and big theta, big omega, the base of the log doesn't matter. All that matters is it's a log. Okay, so hence base of the log does not matter for, big O, etc. Okay. So in this class, we will use, I'm going to use the abbreviation LG to mean log base 2. Right? Sometimes people just write log log to mean log base 10. Ln is log base e. When we're talking about big O, it doesn't really matter. If we want to be specific, I mean, most of the time we'll be using log base 2 in this class, as you can imagine. And I will write LG to mean that. But doesn't matter that much. You notice up here I actually wrote log, not LG, because it doesn't really matter. Okay, so now I can say what the theorem is. Log n is little o of n to the x. Remember, little o means it grows strictly slower than, or like it's kind of strictly smaller than. So as n gets big, right, log n is going to be much less than, it's going to grow more slowly than n to the x. Okay. Well, but then the question is, for what values of x is this true, right? So certainly if x is 1, we know that log n grows more slowly than n, right? And of course, if x is bigger, right? But what about like if x is a half, right? If x is a half, that means square root of n, right? Which grows more slowly, log n or square root of n, right? Anyone have an idea? If I gave you two algorithms and one is log n and one is square root of n, which one would you prefer if n is big? You think square root would be better? You think log would be better? So the answer is log would be better than square root. Well, just think about like the example I gave you. If you have a list of all the humans in the world, like 8 billion, right? What's the square root of 8 billion? I don't know. It's some thousand something, right? And the log I just told you is like 30. So like, yeah, log is better. It turns out log n is little o of n to the x for all x greater than 0. Right? Even if x is like, so a half would give you like square root. Like if x is 1/10, that would give you like the 10th root of n. Turns out log is still grows more slowly than that. Log grows more slowly than n to the, 0.0003. Now in that case, like n would have to get really big before it was actually better, but eventually n to the 0.0003 would end up growing, like crossing log n, and after that point it would always be bigger. I will prove this. If you haven't taken calculus or don't remember it, don't worry, but this is how we can prove it using, like we talked about limits the other day and how that has to do with, basically, right, what does it mean for something to be little o? It means that if I do log n divided by n to the x, the limit is going to be 0. In other words, like, since n to the x is growing more quickly and log n is growing more slowly, like as n gets big, the top is going to be smaller than the bottom, right? And so, and it's just going to get smaller and smaller, and the limit's going to be 0. So the limit as n goes to infinity of, and actually I'm going to use natural log because the base doesn't really matter, right? Over n to the x. Right, if you plug in n for both, you get infinity over infinity, which is indeterminate. We can use L'Hopital's rule. If you recall that, that's where you like do the derivative of both the top and the bottom, and somehow magically it still has the same limit. I don't really know why, but I don't remember why. The derivative of natural log of n is 1 over n. That's why I use natural log, because if we had a different base log, we could still do it, but it would have some like extra constant floating around, and we don't care. And the derivative of n to the x is x times n to the x minus 1. Right, and this is, I can flip, I have 1 over n in the top, so I can move that n down to the bottom, end up with x to the x times n to the x. Oh, I should be writing limit everywhere, right? Limit. And because x is positive, right? This is gonna, as n gets big, the bottom's gonna keep getting bigger. And so it's just gonna be 1 over something, it's gonna go to 0. Okay, that's it. So I guess what, one thing I want to emphasize here is, I think often you take data structures and you learn about like, oh, there's constant time, there's log n, and there's n, right? And you might think like log n, it's kind of halfway in between 1 and n or something, right? It is not. It's way, way closer to 1 than it is to n, in a sense. Like log n is so small, it's not constant. It does depend on n, but it grows really, really slowly. And in fact, more slowly than n to any power. Okay. Cool. Next, let's talk about linear time. All right, this is theta of n. And right, if I have an algorithm that takes linear time, the biggest n that I can process in about a second, again, according to that rule of thumb, right, we're going to say it's about like 100 million. So n equals 100 million in 1 second, approximately. Right, or again, if you had like a list of all the humans on the planet and you wanted to process them using some linear time algorithm, maybe it would take like a minute. It's fine, right? No big deal. So what are some, anyone think of some examples of things that take linear time? Or things that are linear?
Shifting all elements of a list to
Okay.
something again.
Yeah, oh good. I like that. So like I'll say like inserting, at the start of an array or something. Right? So if you have a list and you want to insert something in the beginning, you have to think carefully about how your list is being represented. Right? So like if you do this in Python by default, if you just have a list and you say I want to insert something at the beginning, it takes linear time because it actually has to like move everything over in memory to make room for that new thing and then put it there, right? On the other hand, if you have some kind of linked list structure, you could maybe just add a new node at the beginning pointing to something and you don't have to move anything. And that can take constant time. Python is especially bad at this, actually, where like, and you all may run into this in this class when you're if you choose to implement some things in Python, where it has like nice syntax that hides a lot of things from you, like what's going on, which is nice in some ways, but then also you can accidentally use something that takes linear time or n squared time or something and not quite realize it, right? Like this is a great example, right? If you're just like, oh, I'm just going to insert something here, and you don't think about the fact that really that's hiding this O of n operation. And if you have that inside some bigger loop, right, that could be done. I'll say like, linear search. Right, again, in Python, if you have a list and you check whether something is an element of the list, what does it actually do? It actually loops through the whole list and looks for each thing to see if it's equal to your thing, right? Oh yeah, maybe we should have added to our logarithmic time, like I'll say like lookup. Well, no, I guess like in Python, if you use a set as opposed to a list, I think it's implemented using a hash table under the hood. So now checking if something is in your set is constant time. Whereas if you use a list, it's linear time, and that can be a big difference, right? Other examples I can think of linear time? Yeah, fine.
Finding the maximum or minimum value.
Yeah, so good, finding max or min, or like the sum, of a list. Yeah. Kyle, did you have another example? Grabbing one element from an array. You mean like looking for it or like removing it, you mean? Yes, okay, good. So inserting, yeah, and we'll say like or removing from an array because you have to like shift everything else over. Yep. Yeah, you can actually get pretty clever about coming up with a data structure that implements a list, but that you can add or remove things from either end in constant time. If you've never thought about how to do that, and if you didn't think about that in data structures, it's a nice little exercise to think about how would you implement that. So it can be done. Like Python has a thing in the standard library called deque, D-E-Q-U-E, for double-ended queue, which occasionally is useful if you need to like do stuff to both ends and you want it to be fast. But you know, most standard things, like if you just make a list, well, you can add and remove stuff on the end of the list in constant time, but if you try to do it at the beginning, it's going to be linear time. What else? Another nice example that comes up sometimes is like merging two sorted lists. Right, this is like the thing that merge sort does. After it recursively merges both sides, then it has two sorted lists and it needs to like merge them back together. And it does it just by like looking at the first two things and being like, oh, which is the smallest? All right, let me put that in my output list. Oh, and let's look at the next thing. Oh, this one goes next, right? It's just like kind of going through and like picking out things in order. But since they're both sorted, it can just kind of scan through both of them kind of in parallel and like put things out. But that's only linear time. And that operation ends up being useful sometimes, not just for merge sort, but like in other cases too. Okay. Moving on. The next. I hate this word, but it's in common use, linear arithmetic. So this is like theta of n log n times log n, right? Oh, well, let's see. If you have an n log n algorithm, the biggest input that you could process in about a second is about 4.5 million. Still pretty good, right? Right, again, because like n log n isn't that much worse than n, right? Because the log n is pretty small. So like with n, right, we could process 100 million. Now we can only process 4.5 million, but still it's like on the order of millions, right? It's still a pretty big input that you can deal with. Although, right, this is, you can think about like when you start to get to the scale of like Google, for example, right? Google all the time processes, like, Google engineers like, I need to know, some aggregate statistic about like the entire internet, right? Like our entire search database, right? You can bet that algorithm had better be linear time, not n log n. They also use tons of parallelism, right? You can run it on a ton of computers at once. But even so, probably, well, actually, maybe I take that back because there may be like some sorting that needs to happen. No, so I think like, I guess maybe think of it this way, like n log n plus if you throw a ton of parallelism at it, that's kind of the upper limit of what you can do if you need to process like data on the scale of the whole internet. We'll look, n squared is the next thing we're going to list, and that's super bad. You cannot use an n squared algorithm if you need to process everything on the internet, even if you have a ton of computers and you can like do it in parallel. So what are some examples of things that run in n log n time? Anyone?
There's that sorting algorithm that runs.
Yeah, which one?
On GPU that will search insertion sort, maybe.
Insertion sort does not run in n log n time. Merge sort, yeah, quick sort, merge sort. Oops. Quick sort. Turns out merge sort always runs in n log n time. Quick sort, you can give it bad inputs where it takes longer than n log n, but kind of on average, it still takes n log n time. Yeah, it's funny. Merge sort always takes n log n time. Like, even if you give it a list that's already sorted, it still takes n log n time. Quick sort is kind of the opposite. Quick sort, if you give it a list that's already sorted, it's pretty easy for it to notice that. You can put in a little optimization, have it notice, and like stop early and only take linear time. But it also has some bad cases where it could end up taking n squared time. There's more sophisticated things you can do to kind of get the best of both worlds. But I don't expect you at this point to know or really like be able to explain why merge sort and quick sort take n log n time. That is something we're gonna talk about later in the semester. And of course, like if you just have some log n operation and you do it n times, you know, that's going to be n log n. Those are the only like good examples I know of that are just n log n by themselves. Okay. Quadratic time. This is like theta of n squared. The biggest n you can process if you have an n squared algorithm is 10,000. That's a lot less than 4.5 million, right? You know, we're definitely not at internet scale anymore. But, you know, if you have some data, but not like a ton, but you can do n squared. It's not too bad. But so what are some examples? Does anyone think of examples of things that take theta n squared time? I think one was just, somebody said one earlier. Yes, there are sorting algorithms that take n squared time. Gnome sort. I think, yeah, I think gnome sort is n squared time. I'm assuming nobody remembers what gnome sort is, though.
It's the one where
yeah, you kind of go back and forth. Right, exactly. Yeah. I mean, so like, basically all of the kind of obvious sorting algorithms, like if you asked a you know, a very smart 150 student to like write a function to sort a list, they'd probably come up with an n squared sorting algorithm because they're like, well, loop over everything and then like figure out the right place to put it, and you know, and you pretty easily end up with like two nested loops. N squared, right? All the n log n algorithms are much more clever. I would not expect like a 150 student to come up with them. So like insertion sort, there's something called bubble sort. Yes, gnome sort. But you know, if you only need to sort 10,000 things, it's fine, right? If I like, you know, had a computer and for some reason it didn't have any sorting algorithms like implemented on it already, and I'd had a list of under 10,000 things I needed to sort them, I would just write insertion sort because it's really fast to write. I'm pretty sure I got it right, and I can just, you know, whatever. So, Noah, you have your hand up.
Naive sorting would like naive concatenation also be n squared?
Naive concatenation, what do you mean?
Like if you put the first element onto the end of the list and then another one onto the end, and then so on.
Oh, well, it depends on your model of, if you're talking about like in Python lists, appending something to the end is constant time, so that wouldn't be. But if you're thinking of like Haskell list append or something, like repeatedly appending something to the end would take n squared time. Yeah. But actually, well, a good example of that is in Python or Java, probably a lot of languages. If you like concatenate strings, because strings in most languages are immutable, right? So when I concatenate two strings, it actually has to create a brand new string, like allocate some new memory for the new string and copy the data in from both of the input strings, right? So think about if you have a string and you want to build up a string by repeatedly like sticking one character on the end of it, right? So basically every time I have this string, I stick one character on the end. What it has to do is create a new string, copy over the old string, and then copy the one new character on the end, right? And I do that n times. So it's like 1 plus 2 plus 3 plus 4 plus 5, right? And that is theta n squared. So this is another common way that you can not realize that your program is asymptotically slower than you thought it would be. And they're like all languages have solutions for this. Like Java has something called string builder. I don't remember how Python does it. Python has something like that. That basically gives you a little interface that's like a little array to store characters, and you can stick things in it, and it doesn't have to make a copy. And then at the end, you're like, okay, now give me out a nice an immutable string. So like repeated string append. And in general, like, if I have two nested loops, often, depends what the loops are, right? But if you're just like looping from 1 to n or something and you have two nested things, that's going to be n squared. And then we mentioned this just a second ago, right? When I am repeatedly appending to strings, it's not just like n times n, it's like 1 plus 2 plus 3 plus 4 plus 5 up to n, right? But that, right, there's actually a formula for this, which is n times n plus 1 over 2, right? But that is, theta of n squared, right? Because it's n times n, and then some stuff, some constants, whatever, right? So in this class, I do not care if you know this formula, right? I do care that when you see this kind of thing, this sum where you're adding up 1 plus 2 plus 3 plus 4 up to n, that's going to be n squared-ish, right? You should know that. Now, if you want to learn the formula and kind of understand how to prove the formula, and then, that'll help you remember that it's n squared, but the formula itself is not the important thing. So, because, and why do I say that? Because this comes up all the time. Like, very often, there's something like two nested loops, where the first loop goes from 1 to n, but the second loop doesn't go from 1 to n. It goes from 1 to like whatever the first loop is on. So like if I goes from 1 to n, and then the second loop goes from 1 to I, right? So think about like insertion sort. How does insertion sort work? Well, it loops over every single thing in your input array, and for each thing, it like inserts it into the right place. Well, the first thing, there's nothing to insert into it, just puts it there. It takes one operation, right? The second thing, well, it's got to like scan through and find the right place, which at most takes 2 operations, because like looks at the first one, looks in the second place, right? And the third thing, you might have to do 3 operations, and then 4, right? It follows exactly this pattern of like 1, and then 2, and then 3, and then 4 up to n. It's n squared. Bubble sort is the same, except it goes from n down to 1, because like the first thing you bubble up, you might have to go all the way to the end. But then the second thing, you don't have to go all the way to the end, because now you know the biggest thing is at the end, so you can ignore that. And then you go like n minus 1, and n minus 2. Yeah. Cool. Another thing which you saw on like homework 0, I think, is like, so the number of pairs, of n things. So if I have n things and I want to look at all possible ways of pairing them up, that's going to take n squared. There's n squared many different pairs. And actually, in a way, like these last 2 things are kind of the same. And I'll let you think about why the number of pairs of n things is the same as 1 plus 2 plus 3 plus ... Let's see. In general, I'll do this one more quickly. Right, but in general, if we have like theta of n to the k, where k is some constant. So we talked about when k is 2, but you could have n cubed, n to the 4th, n to the 69, whatever, right? This is things like, let's see, right, if you have k nested loops. Again, it depends what the loops are, but often. This is the number of size k subsets of n things is theta of n to the k. That is, right, n choose k, which is the number of size k subsets out of the number of ways to choose k things out of n, right? This is theta of n to the k. Again, it's not exactly n to the k. It's some big formula. You know, it's like some, but it's going to be some polynomial, and the biggest degree term is n to the k. And I'll just say, you know, theorem. This is kind of obvious, but I'll just say it. N to the j is little o of n to the k when j is less than k. And it's like, this just means like, well, theta of n squared is really smaller than theta of n cubed. It's kind of just obvious, but you could prove it formally by taking a limit and you like cancel some things and it's 0. Let's talk about exponential time. Right, theta of 2 to the n. Right now for n squared, the biggest n we could process in a second was 10,000. Right? For if you have a 2 to the n algorithm, the biggest n you can process in 1 second is 26. Right, so if you have a theta of 2 to the n algorithm, this is really bad. You can do really small things, but it's so small that maybe you could just do them by hand. All right, like it's, yeah. You definitely can't, if you have like 100 things or 1,000 things, forget it. Right, 2 to the 1,000 is very, very large. You tried to run a 2 to the n algorithm on 1,000 things, it'd probably take, like, you would die before it finished, right? The universe might die before it finished, actually. Yeah. What are some examples? Let's see. Hey, can anyone think of examples of things that are 2 to the n? Not necessarily algorithms, but like just a thing that has size 2 to the n. Simon?
Counting all of the numbers you can store in an n-bit number.
Yeah, so like the number of numbers with n bits. Yeah, or the size of the power set. So like the number of subsets of n things. Right, power set.
Sorting a list by retrieving every possible list.
No, good. That's not 2 to the n actually. That's n factorial, which is even worse.
Oh.
Yeah, I mean just like you know, the size of a depth n tree, right? Exponential time, right? 2 to the n is the inverse of log n. So this 2 to the n is about repeated doubling instead of repeated halving, right? So a tree, like if you double the number of things on every level, you go to n levels, you get 2 to the n things. Also, like 1 plus 2 plus, this is another common thing that happens. We're not adding up like 1 plus 2 plus 3 plus 4 plus 5. We're just like adding up bigger and bigger powers of 2. 1, 2, 4, 8, 16. And you go up to some 2 to the n. Right? This is actually equal to 2 to the n plus 1 minus 1. But that's just basically 2 times 2 to the n. So this is theta of 2 to the n. Okay. Another way to think of it is if you do plus 2 plus 4 plus 8 plus 16 all the 2 to the n, like you actually spend half your time doing everything before that last 2 to the n, and then another half your time doing the last 2 to the n. And it's basically just 2 to the n. Right. So theorem, n to the k is little o of r to the n. So n to the k is some polynomial thing. right? N to some power, some constant power. And then on the other side, I'm saying R to the N. So R is some constant, and I'm raising that to the N power, right? But I'm saying this is, for all K greater than or equals 0 and R greater than 1. In other words, right, any polynomial is better than any exponential, right? Even if K is really, really big, N to the 200 power or something, and then my power is like R, like 1.001 to the N, right? Eventually, as N gets big, 1.001 to the N is going to become bigger than N to the 200 or whatever, right? So we kind of have this situation where it's like, here's like log N, here's like N, here's N squared, N cubed, N to the 4th, dot, 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 N to the 200, dot, 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 dot. And there's like this kind of like insurmountable gulf. And then we have like, 1.0001 to the N, 1.1 to the N, 2 to the N, 3 to the N, dot, dot, dot. So this is like, right over here we have like polynomial. And over here we have exponential. And this is sort of the dividing line that we put between like, these are like, okay algorithms, and these are bad algorithms. And in practice, this actually holds really well in practice. That like when there's a reasonable algorithm that, because all the algorithms we know of that are polynomial like don't have actually very big exponents. Like nobody knows of an algorithm is n to the 200, right? 6 I think is the biggest exponent that I've ever heard of that is actually some reasonable thing. So in practice, yeah, if you have a polynomial time algorithm, like life is great. You can do a lot of things with it. If you have an exponential time algorithm, like you just can't really do much. But as we'll learn, like there are some problems where we don't actually know any algorithm other than an exponential one, and we don't think that there's any better ones. So sometimes can't. We don't have time to mention theta of n factorial. So if you have a theta of n factorial algorithm, you should run screaming. It's even worse than 2 to the n. So I think Joust mentioned the sorting algorithm where you look at every possible permutation of your input list and pick the one that is sorted. Yeah, don't do this. All right. I will see you all on Wednesday. Yeah.
What was the n max for the biggest n you could have for polynomial?
Well, I didn't say. I mean, it depends on what k is, right? So I think like with n is like k is 3, it's like maybe 400 or 500, n is 4 like 100, right? So yeah.